So thanks very much, Ashwin, Mike, Ruben, et al., for organizing this conference and inviting me to speak. So also thanks, Mike and Ashwin, for renewing this project. So it's great to have it renewed. So today I'll be talking about a recent work in the framework of this collaboration, mostly with my student, Alireza Parishkar. So, and it's about interaction-driven flat bands and its possible connection to index theorems, but understood in some simple sort of way. So, well, is this supposed to be working? No. Do you guys have a laser pointer that actually works? Oh. Okay, well, anyways, this thing is not working. But it's okay, I guess I'll just do it like this. So, sorry. Oh, I think there was a delay. So yeah, let me start with the motivation and key questions that I want to address. So the motivation comes from a variety of experiments where we observe flat bands. So starting with the good old Landau levels to Moiré systems or nearly flat bands in heavy fermion systems. Also flat bands in line graphs, Gagomel lattices, and whatnot. And we know that the appearance of such flat bands oftentimes is accompanied by a zoo of symmetry-broken phases that we don't really understand in many cases. So in sort of the ambitious goals or questions that we're trying to address in this work is to identify sort of, if such a thing exists, a unifying mathematical origin of the flat bands in all these systems. And we know that flat bands and interactions do lead to interesting fractional quantum Hall effect type phenomena. But in this talk, I kind of want to turn this logic around and see if interactions can lead to the flat bands in the first place with symmetry breaking. And I'll show you some examples. So first, let me talk, though, about non-interacting flat bands and its possible connection to the what I refer to as index theorem, which is not the fancy index theorem. So I'll just start very simple. So the first statement is that, well, let's say we're interested in zero modes of a Hamiltonian, H. So obviously, it's related one-to-one to the zero modes of Hamiltonian H squared. So one, perhaps the most simple example is to consider just matrix Hamiltonians that are like this, where you have two blocks which are different, like rectangular matrices. And if you square this Hamiltonian, so you get this structure where this left upper corner has matrix dimension n plus times n plus, and the lower right corner n minus cross n minus. So it's very easy to prove. There's a proof is basically right here, is that all non-zero eigenvalues of these two objects, d dagger and d dagger d, they come in pairs. So for every lambda plus, there is lambda minus. So, but there should be n plus eigenvalues for d dagger d, let's say, and n minus for d dagger. So there is a mismatch. And the only solution to resolving this mismatch is just to say that, well, there got to be zero modes which are associated with the mismatch in the matrix structure. And so you got these zero modes, and that's basically a kind of poor man's version of index theorems for matrix Hamiltonians. And at least the version of indices, kind of my interpretation of index theorem, kind of practical use to my kind of physics, which is condensed matter physics, is it's sort of an attempt to generalize the notion of the difference in matrix size to, well, infinite dimensional matrices or not matrices at all, to some operators and gauge fields and whatnot. So, and basically a way to do so is just to simply create a structure that counts the, well, the size of the matrix, and then, but such that it generalizes to operators as well. So, for instance, this could be such an index. So say you have a pretty much arbitrary smooth function with which starts at 1 and goes to 0. And then you take this limit, which actually sort of motivated by Fujikawa's method in chiral anomalies. So clearly what it does is simply, if it's a matrix, it's going to count the number, basically the size of the matrix. That's it. And so this gives you the number of zero modes. But the good thing is that it generalizes for infinite dimensional matrices, differential operators, and other structures we may want to work with. And there are other ways to generalize this stuff. Well, for Hamiltonians that don't obviously have this sort of supersymmetric form. Now, suppose we cooked up such a matrix Hamiltonian, which is not very difficult, which does have 0 modes, and we want to create 0 flat bands out of it. So all we got to do is just periodically continue it. Essentially, you take this structure, it obviously has 0 modes, and then you just make it k-dependent in any way you want. In fact, you can, I asked my 11-year-old son to pick, this is the entire code in Mathematica. You can pick any dependence you want here, play around with it, and what you're going to see is a flat band appearing, no matter what. Just because this matrix size counting argument, it doesn't really matter if you have a momentum or not momentum, it's still going to give you 0 modes. So it's sort of topological in this sense, that you can deform d sub k in any way you see fit, and flat bands will remain. So in fact, it was kind of noticed by Bill Sutherland many years ago, almost 40 years ago, who created a specific lattice, which is kind of being drawn here, where you have 2 types of sides, let's say A sides, which are these honeycombs, and B sides, which are these circles. And each honeycomb connects to 6 neighbors, while each circle connects to 3 neighbors, and kind of this matrix mismatch is all you need to create what here referred to as localization of electronic wave functions. But this is just a particular example of this counting argument. So now, as I said, so this doesn't have to be, what I was discussing is sort of tight bonding model, but it doesn't have to be tight bonding model. Let's consider a particle in an arbitrary magnetic field. By arbitrary, I mean it's position dependent. It does not necessarily flat, or let's say periodic, but it doesn't have to be periodic. So, these are 2 Hamiltonians. So this Hamiltonian is the square root of this Hamiltonian, one of the square roots. So you can take either and study, for instance, the question of its 0 modes. And actually, it does have the exact same form as d dagger d d dagger, as I described in the previous slides. So where the left upper corner sort of corresponds to this sigma z being +1, and the right lower corner, sigma z being -1. So in order to calculate the index, you calculate the trace of this operator, basically of this guy h squared. And it's not very difficult. You take any basis you want, let's say plane wave basis. And f, remember, is a function which starts at 1 and goes to 0, however I want. And well, if you just do the algebra, which is, again, not very complicated, so you get this structure. But then you got to subtract from d dagger the kind of dimension of the kernel of this Hermitian conjugate. And if you do so, you will see that only this term contributes to the index. So the message here is the following. So if you have an inhomogeneous, let's say, periodic magnetic field, or any actually magnetic field, and you're interested in having a flat band, so you have to basically quantize the flux of the magnetic field. If it's periodic, it's going to be through the unit cell, but otherwise through the entire space. So you can take actually any magnetic field you like, and you can always, let's say, you fix some random configuration, well, random and let's say periodic, with these triangles being sort of like being repeated. And so it can be tuned to satisfy this constraint, which means it will actually lead you to flat bands if you quantize the flux of the magnetic field through these triangles. So, and this sort of, if you want it, you can say that it's a magic magnetic field configuration. So interestingly, at the classical level, so for instance, if you do create such a field, you'd fine-tune it to this flux being 1, and then you just solve classical problem, basically trajectory of a particle. So it would sort of correspond to a particle going in, not in a circle, it's not cyclotron orbit anymore, it's kind of a spiral, but it's a closed orbit going inside, let's say in this case, triangle. While if you don't fine-tune, I think, I'm not sure I can prove it, but I think you will get basically chaos in some sense. It won't close. Now, what's also interesting is that you can find the wave function of the 0 modes exactly. It's not very difficult. So you take basically what you want to solve, well, let's say you found a condition on the flat band with some A of x and y. And then you have to solve the zero-mode Hamiltonian, and that's it. That's the Hamiltonian. So, and notice that this Hamiltonian only depends on z being x plus iy. It doesn't depend on z bar. So in principle, you can take any function of z bar, multiply it with, well, any other function, and if this guy satisfies the Dirac equation, so will this function. And, well, a solution, as you can check with 5 minutes of algebra, is that the Laplacian of this phi is equal to b being the flux. Well, it's a magnetic field. So, and how do you choose this arbitrary function? Well, you may want to choose it to be doubly, so say you have a magnetic field which is periodic with periods A1 and A2. So you basically want doubly periodic function, it's called elliptic function. And if you also want this condition to be satisfied, there's actually a unique solution to it, which is this. So in some sense, well, you can solve exactly any configuration of a magnetic field with a flat band. And if your magic condition is not satisfied, you're simply, this function is not going to be normalizable. It's not going to fly. So you have, this is an interesting constraint. Now, so this all is kind of interesting in and by itself, in my opinion, but this has nothing to do with interactions. So let's say now I add interactions. And there is a reason to do so. So, I mean, obviously, there are interactions in flat band systems. But also there were, well, papers, including this experimental paper, which basically the elevator pitch here is that, so there are kind of flattish bands in Moiré and twisted ballet graphene, but they saw them flatter than they should be. So according to band structure calculation, you should have something not so flat, but they were flatter. And they kind of address this mismatch by invoking interactions as a mechanism. And then obviously there are many systems known as heavy fermions where you do have heavy electrons, which are basically flat-like bands. And we do know that there is a zoo of phases which we don't really understand very well where they come from, so-called competing phases. So the idea here is actually simple. So let's take the simplest theory we can imagine, say in this particular context. Say we have Dirac electrons with current-current interactions. Actually, it doesn't matter what interactions are, but current-current are easy for my purposes. So remember in the previous slides, I told you that magnetic field can always be tuned to be magic. So, well, if I take this interaction and I decouple it in the Hubbard-Stratonovich field, basically I introduce a bosonic field that decouples this interaction. So this part of the Hamiltonian, of the action rather, is identical to the previous one, except, well, it depends on time. It's quantum fluctuating field. But let's say I forget about quantumness and I look at the, well, basically, as we always do in mean field theories, let's say, we just look at the classical textures. So the point here is I can always pick an average, actually an infinite number of such averages that will give rise to this quantization condition. So which means that I will spontaneously broken symmetry, which will have the form of this sort of, vortex, I don't know what to call this thing, but let's say vortex loops or whatever. So, but basically this lattice, if you want, vortex lattice, which will be spontaneously generated to create a flat band. But obviously it won't be generated if there is no energy reason to do so. So now what I want to show is that there is a model, at least, where I know there is an energy reason to do so. So say we have now a model which has an external field, which I had described before, and interactions, which are now already decoupled in this channel. So, and interactions and the field, they just appear next to each other. So say I have a magic configuration, I would say A bar, which does lead to a flat band. And now I just make a small error. I say, well, let's make it not quite flat, but almost flat. So it's kind of obvious that I can, it's very cheap to correct this, kind of rectify the bands and correct this non-flatness and go back sort of to flat band by just simply picking an average. It's not going to be spontaneous symmetry breaking, because in this case already broken, but still it will be a spontaneous formation of an electronic texture that will go back to the flat band. So now why would you want to do something like this energetically? So I don't know why it's not working. So because, well, there's an argument that flat bands are good energetically. So let's say due to repulsion from other bands, or it depends on your theory. And whatever savings you're going to get are going to be linear in this error, which by construction is small. while the energy cost is quadratic, so I forget about it. So this is good. And so therefore, you get such things. Now, but gauge field is not the only way how you can create flat bands. For instance, you can actually take pretty much any interaction decoupled in the channel that you like, including, for instance, superconductivity. So say you have a Larkin-Ovchinnikov-Uldaferel loft type structure, which is basically periodic order parametry. And you do the usual thing and write BDG action, the Galilean equation. And actually it has the exact same form as before. It has this sort of, if you want, supersymmetric form. And sure enough, you can choose configuration of such superconducting order parameter that would flatten the Bogoliubov bands. But now these would be Bogoliubov bands of superconducting quasiparticles. Again, this is just a proof of principle. You can do it, but it doesn't mean that it's actually going to happen in any system because it will be determined by energetics. So the question is when it may happen. And that's an interesting one. And I think it's particularly relevant to Moiré bilayers. So now, so I don't know if there are any questions up to this point. So, but now I want to move sort of, yes.
So you're taking the, I saw that you have like this vortex lattice with these triangles. And
yeah.
Are you saying that like, so the total magnetic flux is 0, but through one of these triangles you're saying it's quantized to 1? And are you taking some limit where like the magnetic length is much smaller than the triangle size?
No.
Can you try to summarize?
Yeah, so basically, I guess the question is, am I taking any limits on the magnetic field? So I'm dealing with the continuous theory. I'm saying, take any periodic configuration you like. And there's no scale in the theory, actually. There is no notion of small or large or whatever.
Magnetic length, though.
I mean, magnetic length, you choose it. And I'm saying, take, I don't know, 1 Tesla at 1 meter long or whatever. And I will find you a magic texture. If you don't like 1 meter, take 1 centimeter, I'll find you a magic texture. So as long as you have a flux through a unit cell, which is like 1 or 2 or any integer, it's going, well, you will have a flat band. That's the statement. So the length is irrelevant. So you can, it doesn't have to be triangle. It can be, I don't know, square. It can be whatever structure you want. Any arbitrary periodic magnetic field such that it has sooner or later will basically confine your particles and they will go in circles. Well, not quite circles, it will be spirals, but that's pretty much it. So,
but if the field averages to 0 over the whole space, then you don't have any guaranteed 0.
I would say, yeah, I do if I want to. So,
Sorry, the field doesn't average to 0.
I mean, it doesn't have to. I mean, I think in principle I can add any constant and move it around, but it's not a 0 mode. But, well, I mean, as I said, so this is something you can actually verify just simply numerically. So you can pick a texture, adjust it to this level, and you will find that there is a flat band.
So you're saying that there are these down
Yeah. So now, anyways, I don't know what's your point actually. So is there the point? Yeah. So yeah. So before doing more kind of Moiré, so I don't know how much time I have. I'll just stop whenever. So I want to present kind of a general view on this Moiré, which is not necessarily graphene motivated. So general view can be this. Take two kind of isomorph. Okay, I'm not a mathematician, but I'm going to pretend that I am for a sec. So take two basically identical manifolds and move each point in one according to this complicated equation. And this flow psi describes sort of a general diffeomorphism, and that's one geometric. I think Leon Balens actually here, so he presented a theory. There is a single author paper, specifically in the context of graphene, but it doesn't have to be graphene. And then one can enrich this kind of simple geometric structure with metric, matter fields, gauge fields, whatever it is that you like. So, and general observation is that the combined structure have emergent energy scales, may have much smaller than the native scales in the theory. It doesn't have to be actually like graphene with period, these triangles and whatnot. It can be simply theory which is not even lattice theory or not even condensed matter theory. It's any theory where you have some notion of an energy scale in one layer, some notion of an energy scale in the other layer, and you can, if your goal is to suppress them for some reason, such as we pointed out. I mean, I'm not an expert on this, but we just pointed out that obviously there are all kinds of fundamental puzzles where you want energy mismatch between what you expect and what you actually see. But this would be a different talk. So kind of going back to Earth, so if you go back to graphene, so any deformation, it doesn't matter which one. So it can be decomposed into strain and local twist, simply because these are orthogonal vectors and form a basis locally. And that's as simple as that. So, and whatever I'm saying is actually not specific to twist or strain. It's an arbitrary psi. Psi being the field. So you basically take graphene and just imagine you deform it any way you want. So, well, just to remind you, so if you have Moiré twist, so that's what happens. You see the structure. So in my language, the twist will be this sort of flow, this field, psi sub t, where theta is the angle. And the strain will be this. Well, you just kind of conformally transform your lattice. And in the momentum space, as we all know, well, most of us actually working on this know is that, well, I mean, what you do, you kind of rotate, for the twist case, you rotate the Brillouin zone. You have this sort of smaller Brillouin zone and new vectors, 3 vectors that characterize this structure. So, but one observation is actually the twist and the strain are basically the same. It's just 90-degree rotation, actually. So, for instance, if you take, let's say you twist your layer by, I don't know, 1 degree and stretch it by this sort of conformal factor, which is equivalent to it, you will just find basically identical structure, which is just 90-degree rotated. So there is no real reason to consider them separately at all. But in general, you can have both. And then you will have some sort of a bit deformed Brillouin zone with some combination of this vector. This corresponds to the twist. This corresponds to the stretch. And there are 3 vectors, unit vectors, well, not unit vectors, rather. These vectors in the Brillouin zone that define your theory. And actually, Ashwin, I think, or maybe Leon, actually, I think, was the first who wrote, and then Ashwin's paper was very influential also. So a theory, basically continuous theory of these bilayers. So you have, well, obviously you have graphene part, which is just hopping on a lattice. And you have hopping between the layers, AA and AB sort of hoppings. And there, that's what nature gives you, or what your experimentalists give you. And, well, you actually have explicit expressions for these kind of elements, matrix elements, except the overall strength, which are determined by this vector. So this is some geometric structure, which is cumbersome, but not necessarily very complicated. And the key insight, if you forget everything I just said, so just look at this structure. There is a very simple rotation described by this matrix. It doesn't even depend on space, which converts it literally to a gauge theory. I mean, it's not fluctuating gauge theory unless these guys move around quantum mechanically. But it's essentially a theory of Dirac fermions coupled to some external gauge fields, which is this chiral field and this, I don't know what to call it, whatever other field, spin field. But that's how you can write it. And there is an expression for this components. It has kind of time components corresponding to basically electric potential, and has some space components which correspond to magnetic fields. So, and now, I want to understand flat bands which do appear in experiment, for example. I mean, they're not quite flat, and the reason they're not quite flat is because this model actually doesn't have flat bands. It's not chiral model. This was pointed out by Ashwin and collaborators. But if you take a limit where these guys are 0, it brings me back to my sort of supersymmetric model, if you wish. And it does have perfectly flat bands. And, well, if you write it again in terms of these gauge fields, so you basically having no diagonal elements corresponds to having no time components or electric potentials. That's what it kind of means in this language. Now, how do I see these fields in sort of how do I connect it to the previous story? So let me just focus on this part. Yeah, this is the typical structure that you get, but let me not talk about it. So here I have sort of like an intuitive argument how to connect it to anomaly, to chiral anomaly, but in some primitive kind of poor man's version of anomaly. So the initial theory obviously involves 2 plus 1 dimensional fields. You have 2 space components and 1 time component. But if you confine yourself to a flat band, well, time component just drops out. So it doesn't exist. Well, it exists, but you don't care about it. So, and then you get a theory which is now 2 plus 0 dimensional theory, which is anomalous. It has a chiral anomaly, which is actually constrained on the field. So if you can't satisfy this constraint, well, you just don't have a flat band. It's essentially self-consistency constraint on having a flat band in this or actually any other model, which is in fact equivalent to this index theorem that I was describing before. And one can put it kind of to work in specific examples. Let's say you can take uniform twist and just analytically find basically the magic angle, which happens to be this, for example. Or you can take a strain and twist and find this length scale of Moiré periodicity, which is also exact in this model, of course. Or maybe more interestingly, one can take magnetic field and twist, for example. And magnetic field, all it does is just adds to this. I mean, if you add additional fields, all you're doing is just adding gauge fields here. So you're doing nothing else. You're just kind of making your derivative a little more complicated. So you already have your chiral field. Now you're adding like physical field. And the constraint actually is kind of trivial. You just add to your chiral field, you add and subtract the real field, and you quantize it. And out comes splitting of the flat bands into pairs, for example. Also analytical. Which is nice. So the last slide I really have to here is to say that, well, this could be actually a very interesting playground to consider new types of phase transitions, which actually do happen in, obviously, Moiré bilayers. And I don't know if we fully understand them. So one is to say, well, let me consider Moiré bilayer, which is almost flat, but not flat, which is actually the case. It's never flat. So what I'm saying is that depending on the interactions here, for example, it could be, let's say, current interactions, and this time reversal preserving, this one is time reversal preserving field. So you can always find a configuration, create an electronic texture, which in this case it will be an insulating texture, because you create a flat band that's called an insulator, which will correct your textures. And that's one mechanism. So another one is superconductivity. And I think in general it sort of provides an attractive genetic scenario of competing orders whenever you have heavy electrons. And that's what we're kind of working on. So just to summarize, so the key points that I try to convey is that at least these types of flat bands are considered topological and related to a simple version of the index theorem, which provides actually very hands-on practical method for finding magic configurations of field, twists, rotations, whatever it is you want. And I'm more excited about the interaction-induced kind of scenario of creating such textures, and there are quite a few open questions we're working on. Obviously, experiment, I would like to see some verification of that. And there are even some connections to another thing I'm working on, which is chaos. Again, how, like if you do have a flat band and you go back to classical theory, what trajectories do you have compared to non-magic configurations? So this is very interesting. Anyways, thank you very much for your time. Appreciate it.
We have time for 1 or 2 questions. Yeah, wait for the mic.
Thanks, Victor. Just a comment that I think there is a paper by Edward Wheaton pointing out that the critical point between type 1 and type 2 superconductor in 2D is described by a theory like this kind of like arbitrary magnetic field gives the same energy. It seems related, and that's viewed as a 2D version of the Cyber-Wheaton theory. Seems quite related to this.
Well, thank you, Shelley. So it's kind of above my pay grade, so you have people who seem to be excited.
And one quick question is, you said in the interacting case, you said that like in the flat band case, you can just ignore the Hamiltonian term, but that will require that it's flat in a many-body sense. It means even all the many-body states have the same energy, 0?
No, what I'm saying is that, well, look, so say we take any existing actually working theory of phase transitions. So let's say BCS. You take an interacting model and you pretend that the order parameter is actually classical. It's time independent. You fix the configuration, say, I like this configuration, it's going to be classical, and I look at excitations about it all. I'm not aware of any actual theory, maybe with the exception of SYK models, where you really deal with quantum fluctuating fields at the kind of mean fieldish level. So here I'm saying a very simple thing. So if you take a model with interactions, you can always find a mean field configurations which will flatten the bands. So now it's not necessarily mean that it will happen in an experiment, because for it to happen in an experiment, it has to be energetically favorable. But I'm saying, well, there's kind of reason for it to be energetically favorable if you want flat bands. So like there are many examples where it happens, right? So in some sense, superconductor is it's an insulator in this case, which would be flat band of Bogoliubov excitations, or whatever they see in Moiré bilayer. They call it mod insulator, but I don't actually know why it should be mod insulator as opposed to whatever else. So I would say that this is just a new type, basically, of a symmetry breaking mechanism that may or may not pan out depending on the particular model with particular interactions, which will be determined entirely by the energetics. But in the end of the day, I'm just observing there exist configurations of electronic textures which flatten the bands. That's the statement. And I know how to find them. So the rest has to be some numerics for specific models. Yeah.
Let's thank our speaker again. I think it's time for coffee.